course. And so I'm going to not waste time in this lecture discussing the administrative stuff. We have a whole 2-hour tutorial to do that, and today we only have a pre-discussion, so I'm going to do that then. I don't want to waste precious lecturing time, so I'm going to start right away with the actual lecture today. And what I would like to say is that this course is really for the most part a course in homogeneous catalysis, right? We're going to touch on some aspects in heterogeneous catalysis, but mostly we're going to focus our attention on homogeneous organometallic catalysis, and we're going to do a full sequence of these different catalytic reactions. The next thing is this class is mixed, roughly 50-50. There are some people that have taken my inorganic chemistry course in the spring, and there are other people that have not. So I'm going to do it in such a way that it is as accessible as possible for those that have only done the 2000 inorganic course. However, the stuff we did, particularly those that I just taught, last term, I think will be fine because we've discussed like alkyl compounds and stuff like that. So don't worry too much about that. So the first lecture is on an introduction. So let's sort of get the ball rolling. Most of you have seen a figure like this. You know, what does a catalyst do? Well, it lowers the activation energy barrier of a chemical transformation. And it can do so in one step, or which is much more common, it can do that in several steps, as you see here, a multi-step reaction. A good analogy is basically climbing over a mountain. If you want to go from this side of the mountain to this side of the mountain, of course you can climb over the mountain. That's going to cost a lot of energy. Or you can take a shortcut, but you're going to end up at the same place, right? And that shortcut is basically what the catalyst does. It facilitates a lower energy pathway for a chemical transformation in one or more steps, lowering the activation energy barrier. It doesn't in fact participate in the reaction. Well, it participates, but it remains unchanged at the end of the reaction. In other words, after the reaction is concluded, you generally have the catalyst back. Now, we have really three sort of types of catalysis, essentially: homogeneous, heterogeneous, and biocatalysis. We're going to focus in this course mostly on homogeneous catalysis. Heterogeneous catalysis is industrially, I would say, probably more important, although homogeneous catalysis has been growing since the 1970s quite strongly. And a new sort of emerging field is biocatalysis. Now, of course, we all know that we have enzymes in our body, and these are catalysts, basically, to a very large extent. And we can think of those as biocatalysts. In fact, starting from a historical perspective, where does catalysis actually come from? Where did it start? It started around 1823, and this guy, Johann Wolfgang, it was a very typical name in those days in Germany, he was a professor in Germany, there he is, in his very modest little laboratory, was the first to basically, historically have reported some sort of a catalytic transformation. And he found that if you take platinum and oxygen and hydrogen, basically you get some sort of a reaction. And in fact, he reported this to Goethe. And Goethe, who is the same Goethe that is the famous German writer, was also a statesman. And that was really the first appearance of catalysis in the literature from this guy. And there was a lot of sort of speculation for many years what this actually means. But what they very early on identified is that a catalyst, after a reaction has taken place, remains. And they sort of came up with this term catalysis. Berzelius actually defined the term in 1835, so you see a few years after this initial discovery. And Oswald, so that's Berzelius, that's Döbereiner. Oswald, after which the Oswald process is named, nitric acid, actually he was the one that really fixed this notion of a catalyst in chemical literature, start of the 1900s. And he sort of came up with this classical definition that we employ today. So a catalyst affects the rates of a chemical reaction without being part of the end products. In other words, it remains unchanged. And he won a Nobel Prize for that in 1909. So that's Oswald over there. Now, as I said earlier, we've got these three types of catalysis: homogeneous, heterogeneous, and biocatalysis. So a homogeneous catalyst is one that where the products and, well, there's a sort of a textbook definition, where the catalyst is in the same phase as the reactants, okay? And typically this is in the liquid state, right? So everything's in the same phase. Heterogeneous catalyst, generally the catalyst, the catalyst is in a different phase to the reactants. For example, you can have a solid surface, generally a metallic surface, and then you can have gases or liquids, which are the starting materials, which then react at that surface, and you have some sort of catalytic process taking place. That would be an example of a heterogeneous catalyst. I mentioned here, sort of in passing, biocatalysis. I just mentioned a moment ago that we already, most of us, familiar with enzymes and enzymatic reactions. And well, we've sort of all seen this picture, I guess, in first year biology, actually also first year chemistry, we touched on this. And actually, indeed, enzymes can be considered catalysts because they, after all, lower the activation energy barrier. They participate in the reaction, but at the end of the reaction, they sort of regenerate it. Now, this idea of bio-inspired catalysis, in other words, taking enzymes in nature and trying to replicate them in the laboratory, has become a growing field. Textbooks have even been written about it, and there are many examples of beautiful catalysts in nature that do amazing things. You know, for example, in photosynthesis, we have the oxygen evolving complex, which splits water and generates oxygen and H pluses. We have enzymes that, for example, here, one of my favorite examples, hydrogenases, which convert hydrogen to energy, right, reversibly. You have microorganisms that have these enzymes. This is the reactive core of the enzyme, decorated with proteins. And what scientists are trying to do, and what they're trying to do, is take some of these naturally occurring enzymatic processes and replicate them in a lab. And there has been some success in this field. So here we have an example of a sort of a bio-inspired hydrogenase type complex that's fixed onto a nanotube here, which generates energy from hydrogen reversibly, as you can see there. In a similar way to this dinuclear hydrogenase enzyme in nature. So this is a sort of a bio-inspired catalyst, biocatalysis, a growing field, a very interesting field, and a very, I think, a field that is going to gain considerable importance in the future. Now, I want to spend some time talking about heterogeneous catalysts. Although this course is mostly going to be on homogeneous catalysis. As I just said, in a heterogeneous catalyst is typically a solid surface, and we have gas or liquid molecules which somehow interact with the surface. Something happens at the surface and we get the product, as you can see here. In fact, this is the process for, this is a schematic representation of which process? Can someone tell me? What does it look like?
Haber process.
Sorry?
Like some amine forming.
NH3,
Yeah.
H2N2.
Haber process.
Yes, the Haber-Bosch process, precisely. And so these gas molecules, which are very unreactive, right, come onto the surface, it activates them in some way, we get some process phenomenon happening on the surface, and then we generate the ammonia molecules. And what typically happens in a heterogeneous reaction is that we have a process called adsorption, not absorption, adsorption, where these unreactive substrate molecules somehow get activated by the surface. And there's two types of adsorption. We speak of physisorption and chemisorption. Chemisorption is basically a strong type of interaction of this molecule on the surface. Basically what it means is in a chemisorption interaction, a substrate will bind to the surface, and this binding process will perturb the electronic structure quite a lot in the molecule, and basically it's a strong type of, let's say, interaction. Whereas a physisorption is much weaker. You can think of it as a weak van der Waals force, that's basically holding the molecule onto the surface, and that's generally involves quite not so much perturbation in the electronic structure. So that's an important point, these two types of adsorption. So this adsorption process ultimately activates these substrate molecules, something happens on the surface, and we get the products. Now here's a schematic representation on the top here of what's going on. We have some sort of a reactor, we have a catalyst, which is typically a solid. Typically it could be something like iron or iron oxide, carbides, all sorts of things, basically a solid. And we have basically gas or liquid molecules interacting via adsorption with the surface, and something happens on the catalyst surface and we get the product. Now, there are two mechanisms explaining how a heterogeneous catalyst works. The first is called the Langmuir-Hinshelwood mechanism over here, where basically you have two substrates which both get adsorbed strongly on the surface. In other words, they get activated on the surface via adsorption. And then they sort of roll towards each other and form the product, because you have basically an activation step. They're activated, they come together, and then they get released as the product. And the other mechanism is called the Heterogeneous mechanism, where you have one of the reactants or starting materials very strongly interacting with the surface via generally a chemisorption process, so a strong interaction. And the second one, in this case B, as you see here, will interact only weakly with the surface, or even not at all. In other words, you have activation of one of them, and the second one may interact weakly with the surface via physisorption, and basically that is enough to get the formation of the product. So those are the two key mechanisms to explain a heterogeneous catalyzed process. Any questions? All right. Physisorption, chemisorption, adsorption. Strong interaction we call chemisorption, weak interaction physisorption. Two mechanisms for heterogeneous catalyzed reactions, as you can see here. The one involves strong adsorption of the substrates onto the surface. They both interact with the surface quite strongly. We form the product. In the Heterogeneous mechanism, one interacts strongly, the other only weakly, or not even at all, and it just interacts with that activated molecule, and you form the product. And here's basically what I've just said, sort of written out in formal definitions, these two key mechanisms. As I just said, in this mechanism we have strongly adsorbed atoms and molecules held only by weak van der Waals forces, physically adsorbed. So B is, in this case, only weakly bound to the surface. A is strongly bound. Here both A and B are strongly bound, essentially. Now, these are the guys that sort of did it. So this is sort of pretty modern stuff. You know, this field of modern chemistry, of surface chemistry, is very difficult to study because the processes happen very quickly. And it's only in recent times that people, through computer simulations, have actually managed to really understand how gas molecules, or how liquid molecules as well, interact with the surface in a heterogeneous catalyzed process. So that's Langmuir over there, and Hinshelwood, and this is Ile, and this is Vidal. So this is sort of 20th century science. And I should mention this process of understanding surface phenomena and surface catalysis resulted in the 2007 Nobel Prize. So this is a very important field and a very exciting one. Now, as I said at the beginning, heterogeneous catalyzed processes tend to be extremely important industrially. And as you can see in this table, several very important processes, industrial processes, are heterogeneously catalyzed. The Haber-Bosch process, as you can see here, catalyzed by some sort of an iron surface or iron oxide. Other metals work as well. in the synthesis of ammonia. And here are the important applications of these processes. Methanol, Fischer-Tropsch is a process, actually, interestingly enough, very heavily developed in South Africa in the 1950s through to today. So that's a process generating a whole large sort of plethora of interesting organic compounds, a very interesting reaction. Cracking, in other words, taking long-chained organic compounds and breaking them down. This you can do over a clay surface, and so on. Polymerization also works over in a heterogeneous titanium system to make polyethylene, polypropylene, and so on. So heterogeneous processes are really of paramount importance industrially. Now let's look at some examples. Let's start off with a simple example of hydrogenation. So what we basically have is, we can imagine having a catalyst surface, typically a metal, and if you want to hydrogenate an alkene, it typically works over a variety of metals. Maybe some of you have done this in organic chemistry. What works particularly well, for example, is Rayleigh nickel, which is basically just nickel with an extremely high surface area. I've actually worked with it, and Rayleigh nickel has got such a high surface area that if it comes into contact with air, it starts burning. It looks like fireworks. So this stuff really hydrogenates like a bomb, but there's also other surfaces that work. And what you can see is typically what happens. The two substrates basically interact with the surface via some sort of adsorption process. Remember, it could be either the Hinshelwood mechanism or the Vidial mechanism, depends on the reaction. You have an activation, and then basically on the surface, and then you generate the product. And I think it will be nice to sort of look at a video of how this process works, so we can actually see it really. There's some very nice simulations that I found on YouTube, and why not have a look at them, because I think they're quite instructive, and I think that this is a very nice process.
Addition reactions of alkenes. The most important reactions of alkenes are addition reactions. One of the industrially significant examples of addition reaction is the hydrogenation reaction of vegetable oils, which contain unsaturated hydrocarbons having double bonds. In the presence of a nickel catalyst, hydrogen gets added onto the unsaturated hydrocarbons, and they are converted into saturated hydrocarbons. This reaction converts vegetable oils into margarine. For simplicity, we will study the hydrogenation reaction with the simplest unsaturated hydrocarbon, which is ethene molecule. This reaction proceeds through 4 different steps. Initially, ethene molecules are adsorbed on the surface of nickel. Adsorption increases the concentration of ethene on the surface of a catalyst, which helps in increasing the rate of the reaction. During adsorption, the double bond between carbon atoms breaks, and new bonds are formed between carbon and the surface of the catalyst. Simultaneously, hydrogen molecules also get adsorbed onto the surface of nickel. Here, they get broken down into hydrogen atoms. These hydrogen atoms can move over the surface of nickel. Of these hydrogen atoms, the one which diffuses close to the original ethene molecule breaks the old bond between carbon and nickel, and a new bond between the carbon atom and hydrogen atom gets formed. The end of the original ethene, where a new bond is formed, now breaks free of the nickel surface, and eventually the other end also breaks free. Thus,
I think
the product
quite
ethane is now in
a dramatic representation, but a very cute one. Now there's one mistake that she made. Did someone pick it up? A subtle one.
Hydrogen breaking and then
Yes.
diffusing.
She said that it breaks the double bond and it forms a new bond. That's not really what happens. In a process of adsorption, you don't have formal bond breaking per se. You activate the double bond in this case to a very large extent through this adsorption process, but it's not a formal bond breaking, right? So that's sort of, this adsorption process is somehow quite difficult to understand, right? All right, now let's look at some other examples. So that's how hydrogenation works. Again, it works with a lot of metals. You can also do it incidentally with alkynes, triple bonds. And then you look very, very bored. I hope you're all right. The other important process is ammonia. Now we're going to have today, in fact, a nice task sort of devoted to this. So I'm not going to spend too much too much time on it. It is a process developed in the 1930s by Fritz Haber and Bosch. And sort of this is a schematic overview of the process. We'll look at a video in a moment, just so we can see what it looks like. What I'd like to say about this process is without it, world agriculture would only be producing around 2/3 of what we currently can produce. Why is that?
Fertilizers.
Yes, exactly. So this process is extremely, extremely important, I would say, for humanity, for our survival, probably the most important. Here you can see at the bottom, since the Haber-Bosch process in the 1930s, that there's been this population explosion, which has been facilitated by the fact that we can produce more food thanks to the industrial preparation of ammonia. So how it basically works is we generate nitrogen and hydrogen in this step over here, catalytically, and that gets passed through a reactor under high temperatures and pressures over an ion-containing surface, and basically you then distill out the ammonia, you store it, and the nitrogen and hydrogen goes back into the reactor and sort of goes around and around, and you pull out and you condense the ammonia in the process. Now this is sort of energetically what's happening. We have this adsorption process. This would be a typical example of the Hinshelwood mechanism, where the nitrogen and hydrogen are strongly interacting with the surface in a chemisorption process, getting activated, and then moving towards each other and liberating ammonia. Here on the bottom, you actually see the energetic profile of the whole reaction. You basically start over here on the left with nitrogen and hydrogen gas. Those molecules adsorb onto the surface, which is sort of an exergonic, well, it's an exergonic process, 17 kilojoules per mole. And you can see that, so that's the whole molecule adsorbing itself onto the metallic surface. There is an activation energy barrier, and then we really go down, way down energetically, where we've sort of perturbed those nitrogen-nitrogen and hydrogen-hydrogen bonds to a point where you can consider them almost as, well, monoatomic entities. That's very low in energy. And then sort of we go back up. We climb the hill again. We have here in the first step a nitrogen and a hydrogen coming together to form an NH bond, and then an NH2, and finally an NH3. So what's happening on the surface, we have nitrogen and hydrogen being activated through adsorption. We generate these, as you can see here, you can think of it as sort of breaking the bond, although that's not really technically correct. You can rather think of it as just heavily interrupting, if you will, this nitrogen-nitrogen triple bond or hydrogen-hydrogen single bond. And then they move towards each other and basically form ammonia. And you can see the overall process is in fact thermodynamically favored, right? But you need the catalyst to actually do the reaction, because without it, although it's thermodynamically favored, kinetically it won't go under normal conditions.
A question.
Yes.
First, in the process, what metal is the surface? Is usually important?
Iron. Iron, or it also works in fact with iron oxide. Yes.
And can you go back 1 second? The lowest energy there is when the molecules are directly interacting with the surface.
Yes. Yes. and the nitrogen-nitrogen and the hydrogen-hydrogen bond has been interrupted. I wouldn't say broken, I would say interrupted or perturbed. That's a better way of putting it, by the surface. Yes?
When you're going you're lowering energy when there's absorption of the nitrogen and hydrogen.
Yes.
But that means that the activation energy is now even higher, right? As opposed to when it's not adsorbed on the surface. It's a bit
Yes.
counterintuitive.
Yes, that's a good. That's a very good observation. But indeed, but this energy barrier here is very small anyway. You see, this process is exergonic, so it's thermodynamically favored. So that's definitely going to happen, right? Because you're going down in energy, and then this energy barrier here is quite small, so it goes. But it's going to definitely go down in energy into that, so it's going to absorb, even though it results in a higher energy barrier. All right, here's a very nice animation again from BASF of the Haber-Bosch process, which I think is also very nice. So you can visualize what's happening. So today is about looking at nice videos. And fertilizer out of thin air. So BASF, very big company.
One of BASF's first ammonia reactors stands today in Ludwigshafen as an eloquent testimony to the industrial implementation by Carl Bosch in 1913 of the laboratory-scale ammonia synthesis developed by Fritz Haber. The production of this important basic chemical still has its firm place within BASF's chemistry Verbund. To combine the two starting materials, nitrogen and hydrogen, to produce ammonia, the bonds in the diatomic nitrogen molecule have to be broken. Under high pressures of more than 150 bar and temperatures above 400 degrees centigrade, nitrogen adsorbs onto an iron-based catalyst and is split up into atoms. Hydrogen can now be adsorbed and ammonia is produced. The catalyst itself remains unchanged. This reaction generates heat, and therefore the reacting hot gas in the ammonia reactor is cooled with a supply of cold gas. This is achieved with a sophisticated flow system of synthesis gas based on the heat exchange principle. In this way, the so-called equilibrium reaction can be prevented, in which the ammonia tends to decompose again to its constituent elements. The ammonia is collected as a liquid and stored in tanks. The remaining synthesis gas is returned to the reactor and forms more ammonia.
So that's basically quite simply what's happening. I mean, it is an equilibrium reaction. So we use the Chatelier's principle essentially as the reaction's proceeding to condense out the nitrogen, and that pulls the reaction to the right. That's what you saw there sort of on an industrial scale. The next process I want to discuss very briefly is the so-called Fischer-Tropsch process, also very important, and it's really a magical process where you start with syngas, carbon monoxide and hydrogen, generated through coal gasification processes, right? From biomass, coal and natural gas, and steam reformation, you generate a mixture of CO and H2. We call that synthesis gas. And if you pass that over essentially a variety of metal surfaces, iron, cobalt, also metal surfaces which are called carbides, so an iron surface that contains a bit of carbon or cobalt carbides, you get really a broad distribution of organic compounds. You get long-chain olefins, long-chain alkanes, you get ketones, aldehydes, esters, alcohols. I mean, it's just you get it all. It's really an incredible process. And by changing the catalyst surface, you can sort of tweak the product distribution slightly. And you can also play around with the partial pressure of the carbon monoxide versus the hydrogen, and that will sort of shift the product distribution in one direction or another, etc. So that's the basic principle: syngas onto a surface, and you get all of these products. And in fact, someone in the course is going to give us a nice overview in their presentation on this, so we'll have a look at it then in slightly more detail. Again, this process came around the 1930s from Fischer and Tropsch in Germany. And basically what happens is the syngas absorbs onto the surface hydrogen and carbon monoxide. It gets activated, very similar to what we saw moments ago, and you get all sorts of different stuff that can happen. You can have chain growth. You can have, depending on the concentrations, depending on the structure of the surface, depending on all these things, you can get the formation of long or short chain alkanes and alkenes, alcohols, etc., etc. And so it's a process that's been studied quite extensively, but the basic take-home message is metal surface, syngas, you get all these products, and again I have another simulation to show you how this works. This is in fact from the Technische Universität, the Technical University Eindhoven, just down the road. And they in fact do a lot of work with Sasol Technology, which is this company in South Africa that has developed very consistently this process over the last 40 years or so. And they've been doing some simulations.
This animation
So let's have a look.
This animation shows the fate of carbon atoms on different types of ruthenium nanoparticles. Hydrogen decomposes rapidly. However, on a dense planar surface, carbon monoxide decomposes slowly into carbon and oxygen. Since there is a low concentration of free carbon atoms, methane and water are the only products. Only on particles that are large enough to support an open corner with coordinatedly unsaturated ruthenium atoms can the formation of hydrocarbons occur. On the highly reactive ruthenium atoms in this open corner, carbon monoxide rapidly decomposes and generates enough free carbon to sustain a chain growth mechanism. To allow this process to continue, it is necessary for newly formed carbon-hydrogen moieties to move away from the dissociation site. This mechanism of rapid carbon monoxide dissociation and carbon relocation was discovered from quantum mechanical calculations.
So what they've done in this simulation is they've actually used ruthenium metal atoms, which works as well. And this process works with a great many different metallic surfaces. But you saw in that simulation, the other issue is not just the surface, but the actual structure of the surface, right? And that's something I'm not really going to go into, but you know, you have a whole field of surface science really understanding what the surface actually looks like. You know, if it's just a flat surface, if it's got steps in it, kinks, ledges, stuff like that. You saw in that simulation, in order for a chain growth mechanism to actually occur, you need to have a certain configuration on the surface, right? And there are techniques nowadays that you can actually take a surface, characterize it, and understand its topology, which is important in heterogeneous catalysis. Now, let's look at the differences between and advantages and disadvantages between Homo and heterogeneous catalysis. Now, we've been discussing some examples of heterogeneously catalyzed processes. There's many. We've looked at Haber-Bosch, we've looked at Fischer-Tropsch and hydrogenation. Homogeneous catalysts tend to be a lot more robust. In other words, they work at very extreme conditions, typically high pressures and temperatures. Homogeneous catalysts tend to be, you know, much more sensitive, and they work generally at, they're not so robust. But there are advantages and disadvantages to homo and heterogeneous catalysts. So let's have a look at this. The active site is generally poorly defined in heterogeneous catalysts. We just saw that a moment ago. You have a surface, but it's difficult to sort of characterize that surface. A homogeneous catalyst tends to be a well-defined molecular entity, right, that we can synthesize in a lab and characterize by nuclear magnetic resonance, infrared, elemental analysis. We know what we're dealing with. Heterogeneous catalysis tends to be more or less a black box process in a way. Recently, people have started, you know, unlocking the understanding, like we just saw in that simulation, by using computational models and all sorts of interesting surface characterization methodologies like Missbauer spectroscopy and X-ray adsorption spectroscopy and so on, and electron microscopy to understand how these processes work. but generally homogeneous systems are much better understood and more easy to understand because they're well-defined discrete molecules. Generally, homogeneous catalysis takes place exclusively in the liquid state. Gas solids for heterogeneous, in other words, we've got, but you can also in fact have some processes where the substrate is liquid. As I just mentioned, the temperature, this tends to be at a much lower temperature range. You tend to require high temperatures and pressures for heterogeneous processes, which costs energy, right? So that's, again, you can see that sort of as an advantage of a homogeneous catalyst. Now, selectivity is basically, we'll look at this in a moment, but do we make the products we want to make? That's called selectivity. Tends to be very, very high for homogeneous, well-defined systems, and you can tend to steer it very nicely in the direction that you want to in a rational way. Whereas with heterogeneous catalysts, it tends to be sort of, very difficult to control the selectivity because there's all sorts of crazy stuff happening on the surface. I mean, we just saw that simulation of the Fischer-Tropsch process. There's a lot of crazy stuff going on there, and it's difficult to control the selectivity. Heat transfer could be problematic, facile, okay, that's not so important. Product separation. Now, if you're doing a homogeneous catalyzed process in solution, right, so you've got a solvent, you've got the catalyst, you've got the substrate. If you want to, you then have to distill off the products, and so you require complicated distillation and separation protocols. You need to separate out the catalyst. This costs time and money. Whereas with heterogeneous processes, it's kind of simple. I mean, we just saw the setup for the for the Haber-Bosch process. You put in the gas, ammonia is formed, you distill it off, and that's the end of the story. So it's pretty simple to separate it because the catalyst is in fact in the solid state, right? So you've got the solid state, you've got the starting materials, you form the product, and boom, you just separate it. In homogeneous catalysis, it's more difficult. Catalyst recycle, well, this is now basically taking the catalyst and reusing it, right? Tends to be a lot more expensive in homogeneous catalysis because you use expensive ligands generally. And it's difficult and expensive to synthesize these compounds, whereas for the most part, heterogeneous processes are on cheap metal surfaces, like iron and cobalt and stuff like that. So it's much more expensive literally to do not just catalyst recycle, but catalyst synthesis, if you will, is a lot more costly with homogeneous systems generally. And catalyst modification is another important issue. It's difficult with heterogeneous systems because, I mean, you've got a metal surface. How are you going to actually modify and engineer that surface? That's difficult, right? Because like I said, you have to understand how you're going to change the morphology and how that's going to affect the overall catalytic process. Whereas since we're dealing in homogeneous catalysis for the most part with well-defined molecular entities, you can play around with the ligand sphere, that's quite easy. You can play around with metals, you can, and you can understand what you're doing readily. And finally, I think quite importantly, reaction mechanisms. Homogeneous catalysis driven largely by organometallic complexes, one can readily understand the mechanism by doing experimental work, doing certain measurements. You can follow reactions by nuclear magnetic resonance, infrared, etc. Because you're starting from a well-defined molecular entity that you can spectroscopically, in fact, follow a catalytic transformation, whereas you can't really do that very well with a heterogeneous process, or it's much more difficult. And again, this is now an emerging field, right? It's developing, in the meantime, in the last 20 to 30 years, but it's still at its infancy. And we have to rely heavily on computer simulations to understand what's going on. Now, here's an interesting concept, right? And this sort of started, I guess,